Welcome, dear listener. You've made it to a place of rest. Let yourself exhale a little more deeply as the noise of the day begins to fade. And in this gentle quiet, we'll drift into the hidden universe, a world shaped by forces we cannot see, yet feel in every galaxy. There is a kind of matter in the universe that does not shine, does not glow, and does not block light, staying completely hidden from ordinary telescopes. Astronomers know it is there because of the way it pulls on stars, galaxies, and even light itself, revealing its presence only through the gentle tug of gravity on everything around it. Careful measurements of the cosmos show that the matter we can see, such as stars, gas, and dust, is only a small fraction of what exists. A much larger share is this unseen matter, roughly 5 times more abundant than ordinary matter. And beyond that lies an even larger component called dark energy, which quietly drives the accelerated expansion of the universe. The standard picture that cosmologists use to describe the universe is sometimes called the lambda-cold dark matter model. In this framework, dark matter is treated as cold, meaning its particles were moving slowly compared with the speed of light when galaxies began to form, allowing them to clump together and seed structure. One of the earliest clues that something unseen was at work came from the way stars move in spiral galaxies. In the outer regions, stars orbit much faster than can be explained by the gravity of visible matter alone, hinting that a great deal of hidden mass surrounds and permeates these galaxies. When astronomers plot how rotation speed changes with distance from the center of many spiral galaxies, they find that the curves become flat instead of dropping off. This roughly constant speed, far from the bright disk, suggests that an extended, massive halo of invisible matter envelops the visible galaxy and grows more dominant with radius. Long before dark matter became widely accepted, observations of galaxy clusters already hinted at missing mass. The galaxies within some clusters move so quickly that, if only visible matter were present, the clusters should fly apart, implying that a large amount of unseen mass must be holding them together. Light from distant galaxies and quasars bends as it passes near massive objects, creating a phenomenon known as gravitational lensing. When scientists measure how strongly the light is distorted by galaxies and clusters, they find that far more mass is required than can be accounted for by stars and gas alone, pointing to a substantial invisible component. On a larger scale, many background galaxies appear slightly stretched or sheared when viewed across the sky. By carefully analyzing these weak distortions in the shapes of countless galaxies, astronomers can map the large-scale distribution of invisible matter and reveal a cosmic web of filaments and clumps. A striking example of unseen matter at work is found in the Bullet cluster, where 2 galaxy clusters have collided. X-ray observations show hot gas slowed and shocked in one region, while gravitational lensing indicates that most of the mass has passed through and lies offset from the gas, consistent with invisible matter that interacts very weakly and mostly through gravity. More recent, high-resolution observations of the Bullet cluster with modern telescopes provide even sharper maps of the hot gas, stars, and invisible matter. These measurements further support the idea that the unseen component passes largely unimpeded through such collisions and interacts only weakly with itself and with normal matter. The faint afterglow of the Big Bang, known as the cosmic microwave background, is speckled with tiny temperature variations across the sky. The detailed statistical pattern of these fluctuations is very sensitive to how much invisible matter, ordinary matter, and radiation the universe contains, and the measurements strongly support the presence of cold, dark matter. In the early universe, the seeds of cosmic structure were tiny ripples in density, much smaller than the galaxies and clusters we see today. Without the gravitational pull of invisible matter, these ripples would have grown too slowly, and there would not have been enough time for such grand structures to form by the present day. When astronomers map the positions of millions of galaxies, they see that they are arranged in a vast three-dimensional web. Long filaments and walls of galaxies surround enormous voids, and this intricate pattern closely matches simulations that include cold, dark matter, but not models with only ordinary matter and gravity. In many galaxy clusters, detailed lensing maps reveal that the mass distribution extends far beyond the light from stars. These measurements show that the clusters are dominated by huge halos of invisible matter, within which the bright galaxies and hot gas represent only a small fraction of the total mass. Dwarf spheroidal galaxies, especially those orbiting our own Milky Way, are among the most dark matter-dominated systems known. The motions of their few, faint stars indicate that their total mass is hundreds or even thousands of times larger than what is visible, implying that they sit inside massive invisible halos. Galaxies with very low surface brightness, where the visible stars and gas are spread thinly, also show strong signs of being dominated by unseen matter. Because ordinary processes are relatively subdued in these systems, they are often treated as clean environments in which to test theories about how dark matter behaves. Computer simulations that follow the gravitational evolution of cold dark matter particles show a universe where small halos form first and then merge into larger ones. This hierarchical buildup closely resembles the observed population of galaxies and clusters, lending support to the cold dark matter picture. On small scales, simulations of cold dark matter halos often produce steeply rising central density profiles, sometimes called cusps. However, observations of some galaxies suggest flatter inner regions or cores, leading scientists to consider whether feedback from stars and gas or different properties of dark matter might be responsible for the discrepancy. Another puzzle arises when simulations predict far more small subhalos around galaxies like the Milky Way than the number of dwarf galaxies observed. This so-called missing satellites problem raises questions about whether many subhalos remain dark and starless, or whether our understanding of small-scale structure needs refinement. In addition, simulations suggest that the most massive subhalos around a galaxy like the Milky Way should be quite dense, yet the known dwarf satellites appear to reside in less dense halos. This tension, sometimes called the too big to fail problem, invites discussion about the detailed physics of galaxy formation or the possible need for modified dark matter models. Some physicists have explored the idea that the laws of gravity might change at very low accelerations instead of invoking large amounts of unseen mass. These modified gravity theories can reproduce certain galactic rotation curves, but face challenges in simultaneously explaining cluster dynamics and cosmological observations in a unified way. Relativistic extensions of modified gravity, such as theories that add new fields alongside the usual spacetime metric, have been proposed to address cosmological tests. However, systems like colliding clusters, where visible and invisible mass appear spatially separated, remain particularly difficult to explain without invoking an additional unseen matter component. In particle physics, one leading idea is that dark matter consists of weakly interacting massive particles that rarely interact with ordinary matter. These hypothetical particles are motivated by many extensions of the Standard Model, including supersymmetric theories, and would naturally be stable and long-lived. A notable feature of such particles is sometimes called the WIMP miracle, referring to the way a particle with roughly weak force-scale interactions can freeze out in the early universe with just the right abundance. This simple thermal history yields a relic density close to what is observed for dark matter, making the idea especially appealing. Another prominent candidate is the axion, a very light, spin-zero particle originally introduced to solve a subtle symmetry problem in quantum chromodynamics. It was later realized that a large population of axions produced in the early universe could behave as a cold, invisible background that contributes to dark matter. At even lower masses, there is the idea of fuzzy dark matter, where ultralight axion-like particles have such large de Broglie wavelengths that they behave somewhat like waves on galactic scales. This smooth, wave-like behavior could soften the smallest structures and potentially ease some tensions associated with cold dark matter on small scales. Sterile neutrinos, which would be heavier cousins of ordinary neutrinos that do not feel the weak nuclear force, have also been proposed as dark matter candidates. If they reside at keV mass scales, they would act as warm dark matter, subtly altering how small structures form and evolve. Asymmetric dark matter models imagine that invisible particles carry a conserved dark baryon number, analogous to ordinary baryon number. In these scenarios, the amount of dark matter is tied to the same underlying mechanism that created the matter-antimatter imbalance in the visible sector, potentially explaining why their energy densities are of the same order. In self-interacting dark matter models, the invisible particles can scatter off one another with a significant cross-section. These interactions can transfer energy inside halos, smoothing and softening their inner density profiles, while leaving large-scale structure formation largely unchanged. Warm dark matter scenarios propose particles with velocities intermediate between cold and hot dark matter in the early universe. These particles erase the very smallest structures while allowing galaxies and clusters to form on larger scales, leading to a modified pattern of small-scale clustering. Hot dark matter, exemplified by light neutrinos moving at relativistic speeds in the early universe, wipes out fluctuations on small scales by free-streaming through them. Precise cosmological data show that such fast-moving particles cannot provide the main dark matter component, though they do contribute a small fraction of the total. Some theories introduce dark photons, the gauge bosons of a hidden UN symmetry in a dark sector, which can kinetically mix with ordinary photons. Depending on their properties, these dark photons might themselves be dark matter or mediate interactions within a richer dark sector. Atomic dark matter or dark hydrogen models consider a hidden world with particles analogous to protons and electrons interacting through a dark version of electromagnetism. These particles can form neutral bound states that behave as dark matter but support a wider variety of self-interactions and cooling processes. Mirror matter models propose an entire mirrored copy of the standard model, with mirror particles interacting among themselves via mirror forces. These mirror particles would interact only very weakly, if at all, with ordinary matter, except through gravity, potentially contributing some or all of the dark matter. At one time, it was thought that dim stars, brown dwarfs, or stellar mass black holes, collectively known as massive astrophysical compact halo objects, might provide the unseen mass in galactic halos. Careful microlensing surveys, however, have shown that such objects cannot make up the majority of the galaxy's dark matter. Another intriguing possibility is that some of the invisible mass is made of primordial black holes, formed not from stars but from dense fluctuations in the very early universe. These black holes, if they exist in the right mass ranges, could still survive today and contribute to the dark matter population. Constraints on primordial black holes come from many different kinds of observations, including how they bend light, how they might distort the cosmic microwave background, how they would affect star clusters, and the gravitational waves they produce when they merge. Together, these observations carve out which mass ranges remain viable. Some ideas go further and propose that dark matter is not a single type of particle at all, but a mixture of different components. In such scenarios, weakly interacting particles, axion-like fields, and primordial black holes might each provide a fraction of the total invisible mass. Experiments on Earth attempt to detect dark matter directly by watching for rare collisions between invisible particles and atoms in a detector. These searches look for tiny energy deposits left behind when a dark matter particle scatters off a nucleus or, in some cases, an electron. Many of the most sensitive direct detection experiments use large tanks of ultra-pure liquid xenon as their target material. When a particle interacts in the xenon, it can produce both scintillation light and ionization, and the pattern of these signals helps identify and characterize the event. Liquid xenon time projection chambers can determine where in the detector a given interaction occurred and how much energy was deposited. By reconstructing the three-dimensional position, scientists can favor events that happen in the quiet central region and reject those near the edges where backgrounds are more likely. To protect these delicate measurements from cosmic rays, direct detection experiments are usually installed deep underground, in mines or specialized tunnels. The rock overhead acts as a natural shield, greatly reducing the number of energetic particles that reach the detectors. One of the central tasks in these experiments is distinguishing between different types of interactions, because backgrounds can mimic the signals of interest. Researchers work to separate nuclear recoils, which could be caused by dark matter collisions, from electron recoils, which are more commonly produced by natural radioactivity and other sources. As these detectors become more sensitive, they approach a background created by neutrinos from the Sun, the atmosphere, and distant supernovae. This so-called neutrino floor represents a level at which neutrino interactions begin to resemble the signals expected from dark matter, making further progress especially challenging. Recent results from one large xenon-based experiment have set some of the tightest limits yet on how strongly certain weakly interacting dark matter particles can scatter off nuclei. The absence of a signal in this data gently squeezes the range of allowed interaction strengths for traditional WIMP models. Earlier generations of experiments, including previous xenon and liquid argon detectors, steadily improved the limits on dark matter interactions. Each null result narrowed the parameter space and guided the design of newer, more sensitive instruments. Some direct searches are tailored specifically to lower mass dark matter candidates, which would impart smaller recoils. By using lighter target nuclei or innovative detection media, these experiments can probe below the mass ranges where traditional WIMP detectors are most sensitive. Other detectors, such as those based on cryogenic semiconductors, are cooled to extremely low temperatures so they can measure tiny phonon and ionization signals from very small energy deposits. This allows them to explore the possibility of light dark matter particles scattering off nuclei. A different class of detectors aims to measure not just the energy of a recoil but also its direction in space. If such directional detectors can be built with sufficient sensitivity, they could observe an anisotropy that points back toward the direction of the Sun's motion through the galaxy's invisible halo. Indirect searches for dark matter look outward into space for the products of dark matter annihilation or decay. By studying gamma rays, neutrinos, or charged cosmic rays from regions with high dark matter density, such as the galactic center or dwarf spheroidal galaxies, scientists hope to see subtle excesses that might reveal the invisible component. Space-based gamma-ray telescopes watch the sky for very high-energy light that may carry hints of invisible matter. Instruments like these search for gentle excesses or distinctive patterns in gamma rays that could arise if dark matter particles annihilate or decay in regions where they are especially concentrated. On the ground, arrays of Cherenkov telescopes observe faint flashes of bluish light in the atmosphere produced when energetic gamma rays strike air molecules. By reconstructing these air showers, they probe even higher energies than space-based instruments, offering a complementary way to look for possible signals from dark matter in the cosmos. Deep under ice or water, neutrino observatories quietly monitor the passage of high-energy neutrinos, tracking the tiny trails of light they leave behind. If dark matter particles are captured and accumulate inside the Sun or Earth, their annihilation could produce neutrinos that these detectors might see coming from those directions. In orbit, cosmic ray detectors measure streams of particles such as positrons and antiprotons, searching for subtle deviations from expectations. Certain dark matter models predict extra antimatter components in these cosmic rays. But pulsars and other astrophysical sources can also create similar signatures, making interpretation gently delicate. At high-energy colliders, like the Large Hadron Collider, protons are smashed together at enormous speeds to create new particles. If some of the debris consists of dark matter particles that do not interact with the detectors, they will carry away energy, leaving an imbalance in the visible particles that hints at their presence. To interpret these missing energy events, researchers often use simplified models that introduce both a candidate dark matter particle and a mediator linking it to ordinary matter. By comparing collider data with these models, constraints from accelerators can be naturally combined with those from underground and astrophysical searches. When scientists weave together results from direct detection, indirect searches, and collider experiments, they gain a more complete picture of which models remain viable. Large regions of parameter space can be gently ruled out, while the remaining possibilities guide theorists toward more promising ideas. Cosmological observations add another layer of quiet constraint, because dark matter that interacts too strongly with light or ordinary matter in the early universe would leave telltale marks. The patterns we see in the cosmic microwave background and the distribution of galaxies show that any such couplings must be very weak. Studies of possible scattering between dark matter and baryons using cosmological data indicate that such interactions must be extremely small. If they were stronger, they would damp the growth of small-scale structures and blur the fine details of the cosmic microwave background in ways we do not observe. The early universe also allows limits on how much energy dark matter could have injected into the cosmic plasma by annihilating or decaying around the time atoms formed. Extra energy at that stage would have altered the ionization history and temperature, leaving a subtle but detectable imprint on the microwave background. The formation of the lightest elements in the first minutes after the Big Bang gives a precise measure of how much ordinary matter exists. The observed abundances of helium, deuterium, and other light nuclei show that baryonic matter alone cannot account for all the gravitational effects we see, implying a dominant non-baryonic component. Because the lambda cold dark matter model successfully explains the cosmic microwave background, large-scale structure, and galaxy clustering, it has become the standard cosmological framework. Within this model, a non-baryonic dark matter component is essential, even though its microscopic identity remains hidden. By measuring how much structure exists at different scales, scientists can infer how easily dark matter particles can move, or free stream, through the early universe. These measurements help distinguish between very cold, slowly moving dark matter and warmer or more exotic possibilities that would suppress small-scale clustering. Absorption features in the light from distant quasars, known as the Lyman alpha forest, provide a sensitive probe of small-scale structure in the early universe. The fine-grained pattern of these features places limits on the masses of warm dark matter particles, since too much free streaming would smooth out the smallest fluctuations. In self-interacting dark matter models, the strength of dark matter scattering is often expressed as a cross-section per unit mass. Observations of galaxy and cluster shapes, which would become rounder if self-interactions were too strong, restrict how large this cross-section can be on large scales. Galaxy clusters with elongated, elliptical mass distributions offer particularly strong tests of self-interacting dark matter. If the invisible particles scattered frequently, these halos would tend to relax into more spherical shapes than we actually observe, placing quiet limits on how much self-interaction is allowed. Some colliding clusters, including examples like the Bullet cluster, show clear offsets between the distribution of invisible mass and the hot gas seen in X-rays. These separations are used to constrain how strongly dark matter can interact either with itself or with baryonic matter during such dramatic encounters. The internal structures and shapes of dwarf galaxies in the local group provide an important testing ground for self-interacting and fuzzy dark matter models. Different types of dark matter predict different core sizes and velocity distributions in these small systems, making them valuable laboratories for comparing theory with observation. In atomic dark matter scenarios, the dark sector can cool by emitting dark photons, allowing invisible matter to form structures more complex than simple halos. Under some conditions, this cooling could lead to dark disks or compact objects, which would subtly affect gravitational lensing and the dynamics of visible matter. Some theories explore the possibility that dark matter and dark energy are not entirely separate, but instead exchange energy or momentum over time. Such interactions would gently modify both the expansion history of the universe and the way structures grow across cosmic time. If dark matter does interact with dark energy, the effective fraction of dark matter or its equation of state could slowly evolve. Precision measurements of cosmic expansion and structure growth are used to look for such deviations from the simple lambda, cold, dark matter picture. Axion dark matter can be searched for in the laboratory, using resonant microwave cavities immersed in strong magnetic fields. In these experiments, axions passing through the cavity could convert into photons with a very specific frequency, producing a faint but detectable signal. Haloscope experiments, such as ADMX, slowly scan over frequency ranges corresponding to different possible axion masses. By tuning the resonant cavity and listening for tiny excesses of power, these experiments steadily probe more of the parameter space where QCD axion dark matter might reside. Other axion searches include helioscopes, which look for axions produced in the Sun that convert into X-rays in a laboratory magnetic field, and light shining through a wall experiments, which search for photons that transform into axions and then back into photons after crossing an opaque barrier. In 2020, one large xenon-based detector reported an unexpected excess of low-energy electronic recoil events. This anomaly sparked interest in explanations involving solar axions or new dark sector particles, though subsequent work continues to investigate more conventional sources and backgrounds. If dark matter is made of sterile neutrinos, these particles could decay very slowly into an ordinary neutrino and an X-ray photon. This process would create a narrow line in X-ray spectra, prompting careful searches for unexplained emission lines in galaxies and clusters. A tentative X-ray feature around 3.5 keV seen in some datasets once generated excitement as a possible signal of sterile neutrino dark matter. Later observations and analyses, however, produced mixed results and left the true origin of the line uncertain. Primordial black holes, if they provide a fraction of the dark matter, can be constrained by studying the gravitational waves produced when they merge. The rate, masses, and distribution of black hole mergers observed help test whether a significant population might be primordial rather than stellar in origin. Laser interferometer observatories like LIGO and Virgo are especially sensitive to mergers of stellar mass black holes. By examining their event catalogues, scientists can look for signs that some mergers may arise from a primordial black hole population instead of ordinary stellar evolution. Future gravitational wave detectors tuned to lower frequencies, such as space-based observatories or pulsar timing arrays, will be able to probe more massive and more distant black hole mergers. These measurements will further refine the allowed contribution of primordial black holes to the dark matter across a wider range of masses. The density profile of dark matter halos is often summarized by smooth mathematical functions, one common example being the Navarro-Frenk-White profile derived from cold dark matter simulations. This profile features a steep inner cusp that gradually transitions to a shallower slope at larger radii. Alternative profile shapes, such as chord isothermal or inasto models, can sometimes fit observations of real galaxies more closely than classic cusped profiles. Comparing these shapes with predictions provides clues about how baryonic feedback and the microphysics of dark matter influence halo structure. The concept of halo concentration describes how centrally packed a halo is compared with its overall size. In cold dark matter simulations, this concentration typically varies in a systematic way with halo mass and redshift, offering a useful benchmark for comparing theory and observation. Near the Sun, the local density of dark matter in the Milky Way halo is usually estimated to be around a fraction of a GeV per cubic centimeter. This value, though uncertain, is an important input for predicting how often dark matter particles might interact in direct detection experiments. The Milky Way's invisible halo extends far beyond the bright disk and stellar halo, reaching out hundreds of kiloparsecs. Within this vast dark envelope lie our satellite galaxies and tidal streams, all moving under the influence of a gravitational field we can map but not directly see. Long, delicate streams of stars created when smaller systems are torn apart by the Milky Way's gravity act as sensitive tracers of the halo potential. The paths of these streams reveal subtle changes in the gravitational field, helping to outline the distribution of dark matter. Small gaps, kinks, or wiggles in stellar streams can arise when they are perturbed by passing subhalos of dark matter. By studying these features, astronomers can infer the abundance and masses of small, invisible clumps that would otherwise be undetectable. Ultra-faint dwarf galaxies, some of the dimmest galaxies known, are so dominated by dark matter that their visible stars are just a tiny tracer of a much larger mass. These systems serve as quiet laboratories for modeling dark matter and for searching for possible signals in indirect detection. The link between a galaxy's stellar mass and the mass of its surrounding dark halo, often established using abundance matching techniques, ties galaxy formation to the underlying dark matter framework. This relation helps bridge the luminous and invisible sides of cosmic structure. Feedback from processes like supernova explosions and activity around supermassive black holes can reshuffle energy and matter in galaxies. Through gravity, this feedback can also affect the surrounding invisible halo, possibly flattening central density cusps or redistributing dark matter. The pattern of cosmic shear, the correlated distortions in galaxy shapes across the sky, provides one of the most sensitive measures of how structure grows under gravity. By analyzing this pattern, scientists can infer the total matter content, including dark matter, and test cosmological models. Upcoming wide-field surveys with observatories like the Vera C, Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope are designed to measure cosmic shear and galaxy clustering with exceptional precision. These efforts aim to refine our knowledge of dark matter's distribution and its role in cosmic evolution. Time delays between multiple images of strongly lensed quasars arise because light travels along paths of slightly different lengths and through different gravitational potentials. Measuring these delays and modeling the lensing galaxies allows astronomers to reconstruct the mass distribution in and around those galaxies, including their dark halos. Microlensing observations, which track the temporary brightening of background stars as compact objects pass in front of them, place strong limits on how much of the dark matter can be made of such objects. The scarcity of microlensing events at certain mass ranges excludes the possibility that most dark matter is in the form of, for example, Jupiter mass bodies. If dark matter particles annihilated efficiently in the early universe, they could have deposited energy into the cosmic plasma and altered the ionization history. Precise measurements of the cosmic microwave background constrain how strong such annihilation processes can be, limiting many traditional WIMP models. Some dark matter candidates may not be perfectly stable but instead decay over timescales longer than the age of the universe. The soft radiation from these decays would contribute to diffuse backgrounds across the sky, allowing observations to set bounds on how quickly such particles can decay. Dark matter searches also examine the possibility that invisible particles interact with electrons as well as with nuclei. These interactions would leave distinctive imprints in the energy spectra of events recorded by sensitive detectors, offering another channel for discovery. New experimental concepts using superfluid helium, graphene, and other advanced materials are being developed to detect extremely small energy deposits. These technologies aim to probe ultralight dark matter candidates that deposit so little energy that traditional detectors might miss them. Theoretical work on dark matter spans quantum field theory, astrophysics, and cosmology, exploring a vast landscape of models. Many of these theories propose complete dark sectors with multiple particles and forces, within which the dark matter component is only one element of a richer structure. Some models suggest that dark matter might form bound states, analogous to atoms or molecules, within a hidden sector. These dark atoms or dark molecules could lead to phenomena like dark radiation, dark cooling, and even dark stars or dark disks that subtly influence gravitational potentials. In certain interacting dark matter scenarios, oscillations similar to baryon acoustic oscillations in the visible sector can also appear in the dark sector. These dark acoustic oscillations would leave gentle signatures in the matter-power spectrum, providing another way to test such models against observations. If a portion of the dark matter is dissipative and can cool and clump more efficiently, it might settle into thin disks aligned with the visible galactic disks. Such dark disks could contribute to certain kinematic features or mass distributions observed in some galaxies, offering a hint of more complex dark structures. Non-thermal production mechanisms, such as freeze-in or the decay of heavy fields after inflation, allow dark matter to reach the observed relic density without ever being in thermal equilibrium with the early universe. These scenarios open a wider range of possibilities for very weakly interacting particles. In freeze-in models, Dark matter is produced gradually through rare interactions with the thermal bath as the universe expands and cools. The invisible particles accumulate over time, quietly building up the proper abundance without significantly influencing early universe dynamics. Axion-like particles that are not tied to the original strong CP problem can span a wide range of masses and couplings. Some of these fields could contribute to the dark matter or leave subtle imprints in cosmic backgrounds and astrophysical processes, motivating a broad program of searches. Mapping the mass in galaxy clusters by combining strong and weak lensing with X-ray observations provides a detailed picture of how dark matter and hot gas share space. These maps reveal how most of the mass resides in an invisible halo, within which the bright galaxies and glowing gas are embedded. Other cluster collisions, such as those in more complex systems nicknamed train wrecks, present less tidy configurations than the bullet cluster. These systems test both dark matter models and modified gravity ideas, pushing theories to explain their intricate mass distributions. Elliptical galaxies, which do not have the simple rotation curves of spiral galaxies, still show clear evidence of large invisible halos. The random motions of their stars and the way they lens background light both indicate that significant unseen mass surrounds and permeates them. A long-standing relation between a galaxy's luminosity or baryonic mass and its rotation speed provides an important benchmark for theories of gravity and dark matter. Any successful model must reproduce this connection, known through versions like the Tully-Fisher relation, across a wide range of galaxy types. The observation that galaxies and clusters with very different amounts of visible matter can share similar total mass distributions underscores that the unseen component is not simply hidden baryonic matter. Instead, it behaves as a distinct, dominant form of matter that shapes gravitational potentials on many scales. Cosmological measurements of how massive neutrinos suppress small-scale structure show that standard neutrinos cannot account for most of the dark matter. Their total mass contribution is limited to a small fraction, leaving the bulk of the invisible matter to be explained by other particles or fields. Dark matter's role in the reionization era, when the first stars and galaxies ionized the intergalactic medium, is indirect but crucial. By collecting matter into early halos, it created the environments in which those first luminous sources could form and begin to light up the young universe. Simulations that combine the gravitational effects of dark matter with the hydrodynamics of gas have grown increasingly sophisticated. They reveal how strongly baryonic processes, such as star formation and feedback, can reshape the invisible halos, complicating the interpretation of small-scale discrepancies. Some dark matter particles, if captured by stars through scattering interactions, could drift towards stellar cores and accumulate there. In certain models, their annihilation could provide an additional source of energy, subtly modifying stellar evolution in what are sometimes called dark stars. In dense remnants like neutron stars, captured dark matter could build up in the core and, under some conditions, trigger collapse into a black hole. The continued existence of old neutron stars thus sets exotic constraints on dark matter properties, since too much accumulation would have destroyed them. Earth also captures a tiny amount of dark matter as it moves through the Milky Way halo. Though under standard assumptions, the accumulated amount is far too small to produce any measurable geological or geophysical effects. The Sun's motion through the galaxy creates a gentle wind of dark matter in the solar system rest frame. As Earth orbits the Sun, the relative speed of this wind modulates slightly over the year, naturally leading to a predicted annual variation in the rate of dark matter interactions in detectors. The Dharma Libra experiment has long reported a yearly modulation in its detector readings that aligns with the expected phase of the predicted dark matter wind. However, other experiments using different technologies have not observed a similar pattern, leaving the origin of Dharma's modulation as an open and gently debated question in the field. Several new experiments have been built specifically to test whether Dharma's signal can be reproduced under comparable conditions. These follow-up detectors use similar target materials but different setups and locations, and so far, none have confirmed the modulation, adding further mystery to the original observations. Dark matter may also leave subtle traces by interacting with atomic, molecular, or nuclear systems. Some theoretical proposals suggest that tiny shifts in transition frequencies or resonance behaviors could occur, motivating the use of extremely precise measurement tools to search for these delicate effects. Ultralight scalar dark matter, if present, could cause oscillations in fundamental constants such as the electron mass or the fine structure constant. These oscillations would be tiny but detectable with networks of highly stable atomic clocks comparing their frequencies over long periods. An oscillating background of axion-like fields could also create weak, periodic signals in specialized detectors. Experiments using sensitive magnetometers or precision interferometers are exploring these possibilities by tuning into narrow frequency bands where such oscillations might appear. Dark matter substructure, small clumps or streams of invisible particles, could drift through the solar system from time to time. Such features would cause temporary increases or decreases in local dark matter density, potentially producing time-dependent signatures in highly sensitive detectors. The discovery of narrow stellar streams and other finely structured debris trails in the Milky Way suggests that the galaxy's halo has been shaped by many past mergers. These same structures indirectly trace the clumps and distortions in the underlying dark matter distribution. If dark matter had a non-zero pressure or a measurable temperature on very small scales, it could suppress the formation of the earliest tiny halos. This would influence the abundance and internal structure of the smallest galaxies and affect how gas first assembled in the young universe. On the scale of galaxy clusters, the ratio of baryonic matter to total mass offers an independent measure of the cosmic baryon fraction. When combined with data from the cosmic microwave background, these measurements reinforce the need for a significant non-baryonic dark matter component. Strong gravitational lensing by clusters can reveal very small mass clumps within the lensing region. These perturbations to the lensed arcs help test predictions of cold dark matter regarding the number and distribution of subhalos within massive clusters. Flux anomalies in multiply lensed quasar images can also be caused by dark matter subhalos. When the brightness of each image deviates from what smooth lens models predict, it suggests that small, invisible clumps are altering the gravitational pathways of light. The cosmic velocity field, describing how galaxies move relative to the average cosmic expansion, reflects the underlying matter distribution. By measuring peculiar velocities, astronomers can map how dark matter shapes motions on large scales in the nearby universe. Redshift space distortions in galaxy clustering arise because galaxy motions along the line of sight stretch or compress clustering patterns. These distortions provide another window into the overall growth rate of structure and the gravitational influence of dark matter. Understanding the interplay between dark matter and dark energy is key to modern cosmology. Dark matter pulls matter together to form galaxies and clusters, while dark energy drives accelerated expansion, and their combined effects determine how structures evolve over billions of years. Some theoretical models propose that dark matter and baryons might experience gravity differently under certain conditions. This could produce distinguishable signatures in how galaxies cluster or how they lens background light, offering a subtle test of alternative gravity theories. If dark matter felt an additional fifth force, mediated by a very light field, it could cause dark matter to clump differently from baryons. Observations of lensing and galaxy distributions are used to constrain such ideas, since strong deviations would alter well-studied mass patterns. Dark matter could also emerge from exotic processes early in cosmic history. Some models explore production during inflation, from topological defects, or through decays of heavy fields once the universe cooled enough for stable structures to form. The shape of the recoil spectrum in direct detection experiments depends on the velocity distribution of dark matter particles. Non-standard distributions, perhaps shaped by streams or anisotropies, would gently alter how often and how strongly dark matter might interact within detectors. A commonly used baseline in direct detection studies is the standard halo model, which treats the Milky Way's dark matter velocities as a near Maxwellian distribution. More advanced models incorporate halo triaxiality, anisotropies, local streams, and the gravitational influence of the galactic disk. Numerical simulations that form the Milky Way-like galaxies show that the addition of baryons can significantly reshape the central distribution of dark matter. Processes such as baryonic contraction can deepen the gravitational potential, pulling dark matter inward and raising central densities. Conversely, bursty star formation and energetic feedback can create rapid changes in a galaxy's gravitational potential. These fluctuations can push dark matter outward, forming central cores even if the underlying dark matter is intrinsically cold and collisionless. Rotation curves and mass profiles of small galaxies are important tests of these baryonic feedback mechanisms. If feedback alone cannot explain the observed cause, scientists may look to alternative dark matter physics to resolve the discrepancy. Future 21cm surveys, which observe the hyperfine transition of neutral hydrogen at high redshift, will probe how the first structures formed. These measurements are sensitive to dark matter properties that influence the timing and temperature of early cosmic heating. Some models of annihilating or decaying dark matter are constrained by the spectrum of the extragalactic gamma-ray background. Too much high-energy radiation from these processes would produce an observable excess across the sky. The smoothness of the diffuse gamma-ray background over a wide range of energies places strong limits on many dark matter models, with efficient annihilation or decay channels. These observations help narrow the allowed parameter space for invisible particles. Specific dark matter candidates that create charged particles in their annihilation or decay must also satisfy tight constraints from the cosmic microwave background. Any appreciable energy injection at early times would disturb the ionization history and spoil the measured CMB pattern. Light dark matter that interacts primarily with electrons rather than nuclei is accessible to experiments originally designed for neutrino detection. These detectors, with their low thresholds, are now being used to explore sub-GeV dark matter interactions. Accelerator beam dump experiments produce intense streams of particles that pass through shielding and into downstream detectors. If dark sector particles are created in these environments, they might decay or interact in subtle ways detectable by specialized instruments. Experiments at the so-called intensity frontier look for very rare processes and extremely weak couplings. These studies complement collider searches by probing parameter regions where dark matter might interact too faintly to be seen in high-energy collisions. Some models suggest that dark matter interacts more strongly with certain types of standard model particles, such as leptons, quarks, or specific families, leading to unique experimental signatures. Observations across different platforms can help distinguish among these possibilities. If dark matter belongs to a broader dark sector with multiple components, it might be accompanied by a form of dark radiation. Such radiation would behave like an additional relativistic species, subtly shifting cosmological observables such as the effective number of neutrinos. Cosmic microwave background data and Big Bang nucleosynthesis measurements constrain the total amount of dark radiation allowed. Any extra relativistic degrees of freedom must fit within these bounds, limiting the possible size and nature of hidden sectors. Small departures from Gaussianity in the large-scale matter distribution could point to unusual interactions or initial conditions in the dark matter sector. Precision surveys are beginning to search for these higher-order signatures in cosmic structure. Some proposals suggest that dark matter on galactic scales might form a Bose-Einstein condensate. In such scenarios, the wave-like properties of the condensate influence halo cores and could help explain certain smooth central density profiles. In fuzzy dark matter models, interference patterns and solitonic cores naturally emerge in simulations. These wave-driven effects provide potential observational signatures, such as gently oscillating central densities or distinctive velocity structures in small galaxies. The diversity of galaxies that appear to contain unusually little dark matter has sparked careful re-examination of how mass is measured. These rare systems challenge standard formation models and encourage deeper study of tidal interactions, feedback processes, or even non-standard dark matter behavior. A few reported galaxies appear to have extremely low dark matter content based on their internal dynamics and observed mass. If confirmed, such galaxies may have experienced strong stripping, unusual formation paths, or other events that separated stars from their original halos. Galaxies with anomalously low dark matter content compel scientists to re-evaluate assumptions about how galaxies acquire and retain their halos. They also offer a proving ground for testing alternative theories of gravity or modifications to the standard dark matter paradigm. Strong lensing clusters with prominent arcs and multiple images allow detailed reconstruction of subhalo populations. These strong lensing analyses provide an independent test of the predicted number of dark matter substructures in massive clusters. Line intensity mapping, a technique that observes the combined emission from many unresolved sources, provides a novel way to trace large-scale structure. Because it captures integrated light from cosmic volumes, it can reveal clustering patterns influenced by dark matter. Cross-correlating different cosmological probes such as galaxy surveys, gravitational lensing maps, and lensing of the cosmic microwave background helps isolate the true matter distribution. This combined approach reduces systematic uncertainties and strengthens constraints on dark matter. The gravitational lensing of the cosmic microwave background provides a direct map of how matter, both visible and invisible, deflects the oldest light in the universe. These lensing patterns encode information about the integrated mass distribution across cosmic time. When CMB lensing data are combined with galaxy clustering measurements, they help break degeneracies between cosmological parameters. This joint analysis sharpens estimates of matter density and the amplitude of fluctuations, improving our understanding of dark matter's role. Decades of dark matter searches have yet to reveal a conclusive direct signal, motivating a broader exploration of masses and interaction strengths. Researchers now investigate candidates ranging from ultralight fields to particles far heavier than originally imagined. Ultralight dark matter candidates can have masses many orders of magnitude below the electron mass, while super-heavy candidates can reach scales far beyond what colliders can directly probe. This enormous range highlights the need for diverse experimental strategies. No single type of detector or telescope can cover such a broad parameter space, so the worldwide effort involves multiple approaches. Each method: direct detection, indirect searches, colliders, astrophysical probes covers different regions, and together they steadily constrain the possibilities. The absence of clear signals has encouraged theorists to imagine richer hidden sectors with multiple interacting components. These ideas inspire new detection concepts that differ from the traditional focus on weakly interacting massive particles. Some scientists explore the notion that dark matter could be a mixture of different species rather than a single particle. If true, the cosmological abundance could arise from multiple production mechanisms and interactions in a shadowy, multi-component sector. Historically, astronomers have inferred the existence of unseen objects before observing them directly. The eventual discovery of Neptune after noticing irregularities in Uranus's orbit is often invoked as an analogy for how dark matter reveals itself through gravitational effects. The long-standing debate between unseen matter and modified gravity has stimulated productive research in both directions. These investigations refine tests of gravity at galactic and cosmological scales and challenge theorists to sharpen predictions for dark matter models. Dark matter is essential for explaining why galaxies and clusters have the structures they do. Its gravitational pull shapes the environments where gas cools, stars form, and planets eventually emerge, influencing the entire landscape of cosmic evolution. In numerical simulations, altering the nature of dark matter from cold to warm to self-interacting to fuzzy changes how galaxies assemble and what their internal structures look like. Comparing these simulated universes to observations helps identify which models best match reality. Because invisible matter outweighs luminous matter in most galaxies, it governs orbital paths, stabilizes disks, and determines how satellites move within their host halos. It creates the gravitational scaffolding upon which visible structures are built. Dark matter halos and the gravitational potentials they generate also determine how light travels past galaxies and clusters. This lensing effect allows astronomers to map the invisible component even when it interacts only through gravity. The search for dark matter drives advances in low background detection technologies and cryogenics, along with innovations in data analysis and statistical methods. These technical achievements often find applications in other fields of physics and engineering. Dark matter experiments require extremely pure materials and careful noise suppression. Pushing these limits continually improves scientific instrumentation and expands the frontiers of what tiny signals can be measured in the laboratory. Both Bayesian and frequentist statistical approaches are widely used to analyze data from dark matter searches, carefully accounting for backgrounds, systematics, and uncertainties ensures that any potential signals are interpreted with appropriate rigor. Null results, though seemingly quiet, are highly informative. Each new limit excludes regions of parameter space, guiding theorists toward more promising models and helping experimentalists design the next generation of searches. International collaborations, conferences, and coordinated research plans reflect the scale of the dark matter challenge. The field brings together astrophysicists, particle physicists, cosmologists, and engineers in a shared effort to uncover the nature of the invisible. Dark matter is now a standard topic in physics education, appearing in undergraduate and graduate courses. Students learn about its gravitational fingerprints long before any direct particle detection has been achieved. The public remains deeply fascinated by dark matter because it represents a profound cosmic mystery. Most of the matter in the universe is something we cannot see, yet it shapes galaxies and influences the fate of cosmic structure. Outreach programs, documentaries, and popular science books help communicate the excitement of this mystery. They show how much we have learned about the universe and how much remains to be discovered about the unseen. Future direct detection experiments aim to increase sensitivity by using larger detectors, lower backgrounds, and improved energy resolution techniques. These advances will either discover tiny nuclear or electron recoils or push the reach of experiments down toward the neutrino floor. Next-generation gamma-ray, X-ray, and neutrino observatories will probe unexplored energy ranges and astrophysical environments. These telescopes will tighten constraints on annihilating or decaying dark matter and may reveal subtle signals hidden in cosmic backgrounds. Wide and deep galaxy surveys will greatly expand the census of faint, dark matter-dominated galaxies. These discoveries will provide new targets for indirect detection and new testbeds for models of structure formation. Precise measurements of cosmic expansion and the growth of structure using multiple tracers will continue testing the consistency of the standard cosmological model. Any deviations may point toward new physics in the dark sector or modifications to gravity. Novel ideas for detecting local dark matter include studying the motions of planets, spacecraft trajectories, and even subtle oscillations in gravitational systems. These approaches push the boundaries of how gravitational effects might reveal the invisible. Laboratory searches for new light bosons, millicharged particles, or other dark sector states complement astrophysical probes. Together, these efforts cover a wide range of masses and couplings, ensuring no plausible region is left unexplored. Some hidden sector theories suggest that dark matter carries charges confined to a dark version of electromagnetism. If so, it could form composite states, dark atoms, or bound structures, whose collective behavior would leave gentle gravitational signatures. Dark matter mini-clusters or microhalos, if they exist, might occasionally pass through the solar system. Such encounters could temporarily boost local dark matter density and lead to fleetingly enhanced interaction rates in sensitive detectors. Exotic compact objects such as boson stars, which would be made of scalar fields rather than baryons, might act as unusual gravitational lenses. Their presence could be inferred from distinctive light-bending patterns, unlike those produced by ordinary stars or black holes. If interactions between dark matter and ordinary matter depend on environmental factors such as local density or temperature, they could vary across space and time. This possibility encourages experiments to look for spatial or temporal modulation beyond simple annual cycles. Some dark matter theories link the invisible sector to other unresolved questions in physics, such as the origins of neutrino masses, the matter-antimatter asymmetry, or the hierarchy problem. A discovery in one area could illuminate several fundamental mysteries at once. Finding dark matter would likely spark a new era of physics centered on the hidden sector, just as the discovery of the neutron or the neutrino opened vast fields of study. Identifying dark matter could reveal an entire landscape of new particles and forces. Even if direct detection remains challenging, dark matter's gravitational influence will continue guiding our understanding of cosmic structure. It provides a benchmark against which any alternative theory must be measured, anchoring the framework of modern cosmology. As cosmological measurements improve, tensions between different datasets, such as disagreements about the Hubble constant or the amplitude of matter clustering, have emerged. Some proposed solutions involve novel interactions or behaviors in the dark sector. Adjustments to how dark matter clusters or interacts on specific scales may help reconcile these tensions. Such ideas motivate theorists to refine models and observational strategies to test them. The possibility that the dark sector includes multiple components, dark matter, dark energy, and perhaps additional fields, suggests that our current picture of the universe is likely incomplete. Each new observation provides a chance to glimpse more of this unseen realm. Despite many open questions, the lambda-cold dark matter model successfully explains a broad array of observations from the early universe to present day. It remains the standard against which alternative ideas are compared. Although we cannot yet see what dark matter is made of, its gravitational fingerprints appear everywhere, from the rotation of galaxies to the pattern of cosmic structure. This consistent evidence leaves little doubt about its pervasive presence throughout the cosmos. Ultimately, solving the dark matter puzzle will likely require progress on multiple fronts: laboratory detection, astrophysical observation, and theoretical insight. Each approach complements the others, gradually illuminating the nature of the unseen. Until the invisible particles themselves are detected and understood, dark matter remains a central, unsolved problem in physics and astronomy. Its resolution will unlock deeper understanding of both the smallest constituents of matter and the largest structures in the universe. In the soft quiet of the night, you can imagine the universe stretching gently in all directions, threaded with something unseen that holds it together. Dark matter becomes not just a scientific idea, but a calm, steady presence woven through the spaces between the stars. It is comforting to think that even though this invisible mass does not shine or glow, it has been there from the beginning, guiding the growth of galaxies. Its gravity has helped shape the cosmic landscape that we now look up at in wonder. The same hidden substance that bends light and anchors clusters has also helped create the conditions for stars, planets, and eventually life. Our own existence is quietly linked to something we cannot see, a reminder that the essential can sometimes be invisible. As the universe expanded and cooled, dark matter was already at work, slowly gathering clouds of gas and dust into deeper wells of gravity. Within those wells, galaxies could form and evolve, building the structures that make the night sky so rich and varied. Even though its particles remain unknown, dark matter's role is evident in the way galaxies rotate, clusters hold together, and large-scale patterns emerge. Its gravitational imprint is like a signature written everywhere across cosmic time. The notion that most of the matter in the universe does not emit or absorb light invites a gentle kind of humility. Our senses and instruments, powerful as they are, still only reveal a small portion of what truly exists. Astronomers have built a compelling picture of dark matter not by seeing it directly, but by tracing its effects on what can be seen. In the quiet arcs of light and the steady motions of stars, the unseen leaves its clear and patient mark. The idea that unseen mass sculpts the cosmic web can feel almost poetic, an invisible framework on which galaxies hang like tiny lanterns. The luminous structures are just the decorations. The dark matter is the scaffolding beneath. As observations have improved, from early telescopes to modern space observatories, the case for dark matter has grown stronger. Each new survey, each refined map, adds another piece of evidence that this hidden mass pervades the cosmos. In simulations, when scientists include dark matter and let gravity run its course, virtual universes emerge that resemble our own. This quiet agreement between computation and observation suggests that the invisible ingredient is an essential part of the recipe. The same simple model, with cold, non-baryonic dark matter, explains patterns in the cosmic microwave background, the distribution of galaxies, and the behavior of clusters. This consistency across so many scales gives the model a calm, reassuring strength. At the same time, small tensions and puzzles remain, like gentle ripples on an otherwise smooth surface. These details encourage scientists to look more closely, to wonder whether dark matter might have subtle properties not yet fully captured. Some galaxies appear to have unexpectedly large cores or fewer satellites than simple models predict. These discrepancies are not loud contradictions, but soft hints that either baryonic physics or new dark matter behavior could be at play. The possibility that dark matter could interact with itself or cool in special ways adds richness to the picture. Entire hidden processes may be unfolding in the dark sector, leaving only faint gravitational traces for us to interpret. There is also room for the idea that multiple kinds of dark matter coexist, each contributing in a different way. Much as ordinary matter includes protons, neutrons, electrons, and more, the unseen sector might be varied and complex. In this sense, dark matter may not be a single, simple answer, but a gateway to an entire realm of physics. Its discovery could reveal a broader family of particles and forces, operating quietly alongside the familiar ones. Because dark matter touches so many areas of science, its study connects distant fields together. Cosmology, astrophysics, particle physics, and experimental techniques all meet at this shared question about the nature of the unseen. The search for dark matter has already advanced our capabilities in low-noise detection, data analysis, and instrumentation. Even without a confirmed signal, these developments have enriched experimental science in many gentle and unexpected ways. In classrooms, students learn how dark matter's gravity helps galaxies form and rotate. The concept has become part of the basic language of modern physics, showing how deeply it is woven into our understanding of the universe. Public curiosity about dark matter reflects a broader human fascination with the unknown. The idea that most of the matter around us is invisible creates a quiet sense of mystery that invites contemplation rather than fear. Books, documentaries, and public lectures transform complex research into shared stories about the hidden cosmos. Through them, the question of dark matter becomes part of a larger cultural conversation about what lies beyond the limits of sight. Future detectors, more sensitive than ever, will be able to listen even more carefully for tiny signals of dark matter interacting with ordinary matter. Whether they find a clear sign or push the limits further, they will gently guide theory forward. New telescopes watching high-energy radiation will continue to look for telltale patterns that might betray annihilations or decays in regions dense with dark matter. Even subtle absences of such signals help refine our expectations. As more dwarf galaxies and faint systems are discovered, astronomers gain fresh laboratories where dark matter's influence is especially strong. These quiet galaxies, dim but heavy, offer some of the clearest views into how the unseen shapes the seen. Precision measurements of how the universe expands and how structure grows over time provide another avenue for understanding dark matter. If its properties differ from the simplest expectations, these delicate observations may reveal small but telling deviations. The idea of examining planetary motions, spacecraft paths, or tiny gravitational anomalies to detect dark matter nearby is a testament to human creativity. Even the most gentle accelerations and shifts become potential clues in the broader search. In laboratories, experiments continue to push the frontier of what can be measured, probing ever lighter particles and ever weaker interactions. Each null result, though quiet, narrows the field and helps focus attention on what remains plausible. Some theories envision dark matter with its own charges and bound states, forming dark atoms or more complex structures. These hidden formations would not emit light, but they could subtly shape gravitational fields and cosmic history. Small, dense clumps or microhalos of dark matter, if they exist, might drift silently through the galaxy. Encountering one could momentarily enhance the local flux of dark matter particles, offering a rare opportunity for detection. Exotic objects such as boson stars or dark cores, built from fields rather than ordinary matter, might bend light in peculiar ways. Observing their lensing patterns could reveal structures that are invisible in every other sense. If dark matter interactions vary with the environment, its behavior in the dense centers of galaxies could differ from its behavior in the thin outskirts of halos. This gentle dependence might help explain some subtle mismatches between simple models and detailed observations. The possible connection between dark matter and other deep puzzles like why the universe favors matter over antimatter adds another layer of intrigue. A single discovery in the dark sector might illuminate multiple questions at once. Should dark matter be identified and studied in detail, it would open a new chapter in our understanding of fundamental physics. The hidden sector would become a field of its own, with new particles, forces, and phenomena to explore. Yet even if direct detection remains elusive, dark matter's gravitational role ensures it will stay central to cosmology. Any alternative theory must still match the intricate patterns of structure that this invisible mass so naturally explains. As measurements grow more precise, small tensions in cosmological data hint that something subtle might be missing from our current picture. Whether these tensions arise from dark matter, dark energy, or something else, they encourage quiet exploration. Some models adjust how dark matter clusters or interacts, hoping to ease these discrepancies without overturning the entire cosmological framework. These gentle refinements keep the standard model flexible while remaining grounded in observations. The idea that the universe may contain multiple unknown components, dark matter, dark energy, and perhaps additional fields, reminds us that our current model is likely an approximation. It is accurate enough to navigate by, yet incomplete enough to invite further discovery. Despite these open questions, the lambda cold dark matter model continues to align remarkably well with data across many scales. It serves as a stable foundation while leaving room for new layers of understanding to be added. At the heart of the mystery lies a simple, persistent question. What substance creates the gravity we see, yet hides so completely from our telescopes and detectors? This question sits quietly at the center of much of modern cosmic research. Answering it will require patient collaboration between theory, experiment, and observation. Each new limit, each improved map, each refined model brings us a little closer to seeing how the invisible is woven into the fabric of reality. Until then, dark matter remains a gentle puzzle that connects the smallest scales of particle physics with the largest structures in the cosmos. Its presence is felt in the way galaxies spin and clusters hold together, even though its nature stays veiled. In this incomplete knowledge, there is a certain peace. We are surrounded by mysteries that do not demand immediate resolution. The cosmos is vast, and understanding it fully will take time, care, and quiet persistence. When you look up at the night sky, you see only the bright traces of a far deeper structure. Behind the stars and galaxies, dark matter's gravity shapes the cosmic web, holding everything in a soft, unseen embrace. The search for its identity continues across laboratories, observatories, and simulations, each approach listening for different kinds of whispers from the invisible. Step by step, the outlines of the hidden sector become a little clearer. For now, it is enough to know that the universe we inhabit is richer than what light alone can reveal. The unseen mass that steadies galaxies and sculpts clusters is part of that richness, a quiet companion to the luminous sky. As thoughts drift and the mind softens, Dark matter can be held as a gentle reminder that reality extends beyond our immediate senses. There is more to the cosmos than we can see, and more to understand than we yet know. In that awareness, there is room for curiosity and calm, for both questions and rest. The universe carries its secrets patiently, and we move toward them slowly, guided by faint clues and quiet determination. While you settle into stillness, the idea of dark matter can fade into the background like a soft, steady hum. It remains there, holding galaxies and clusters together, while the surface of your thoughts becomes smooth and quiet. The stars above continue their paths within vast, unseen halos, and the cosmic web stretches on in every direction, shaped by forces we have not yet fully named. All of it goes on whether we are awake or asleep. In this moment, you do not need to solve the mystery or trace every filament of the cosmic web. It is enough to rest in the knowledge that the universe is held together by something invisible and constant. As you breathe gently, the questions about dark matter can drift to the edges of awareness, like distant constellations. The unseen mass remains, patient and steady, while your own thoughts grow softer and slower. The cosmos will continue to evolve, and scientists will continue to listen for signals from the dark sector, refining their instruments and ideas. But here, in the quiet of now, those efforts can simply be part of a larger, peaceful story. Dark matter's presence, though unknown in detail, offers a sense of continuity and structure running through the universe. It is a reminder that even in the deepest darkness, there is an underlying pattern guiding the stars. And as you rest, you can let that thought become gentle and distant, like a dim glow beyond the horizon of the mind, part of a vast and comforting universe that continues on in silence.